Say we want to determine a load resistance that maximizes our power output, and then numerically determine the value of our maximum power output. In the circuit below, we have a 180 volt source supplying a potential to a 30 ohm resistor. This 30 ohm resistor is then connected to a 150 ohm resistor and our load resistor, which exists in a parallel configuration. To begin, we have to determine our equivalent, or our Thevenin resistance, that would maximize our power output, and prescribe that value as our load resistance. To do such, we will disconnect our load resistance and short our voltage source and look into our circuit to determine our equivalent resistance. In doing such, we'd have the following circuit, where our 30 ohm resistor and 150 ohm resistor now exist within a parallel configuration. Thus, our equivalent resistance would be 30 times 150 ohms per 180 ohms, or we'd have an equivalent resistance of 25 ohms. Thus, our load resistor would have a value of 25 ohms. Now, to determine the numeric value of our maximum power transfer to a load resistance, we have to determine our open circuit voltage via voltage division. That is, if we remove our load resistor and look at our circuit, our open circuit voltage existing between terminals A and B would simply be our voltage potential across our 150 ohm resistor. That is, VOC would be 150 per 180 quantity times 180 volts, or we'd have 150 volt potential existing across terminals A and B with our load resistor removed. Lastly, to determine our maximum power, all we have to do is calculate our open circuit voltage squared for 4 times our load resistance, which would be equal to 150 volts squared for 100 ohms, or 225 watts.